New York's newest neighborhoods are not all built on Manhattan. Parts of them are built above moving trains. Walk through Hudson Yards or Manhattan West and everything feels permanent. Glass towers, restaurants, trees, public plazas, and streets crowded with people. Yet beneath sections of that polished city, there is no ordinary ground. There are active railroad tracks carrying trains into and out of Penn Station. The neighborhood above is standing on artificial land suspended over a transportation system that was never allowed to stop. And that is the real engineering mystery. The surprising part is not simply that a platform can hold skyscrapers. It is that engineers had to build an entire city in the air while keeping another city alive underneath it. By the end of this video, you will understand how tower loads reach bedrock through narrow gaps between tracks, how trees survive above an industrial heat source, and why maintenance may be the hardest part of the whole project. To understand the system, follow one commuter train approaching Manhattan. At track level, the train enters a working rail corridor. Above it, people cross a landscaped plaza without realizing they are walking across the roof of an enormous bridge. The train needs clearance, ventilation, power, signals, maintenance access, and a safe route into one of the busiest rail hubs in North America. The neighborhood above needs foundations, roads, water, electricity, drainage, trees, fire protection, and enough structural capacity for towers weighing hundreds of thousands of tons. Neither system can be treated as secondary. The railroad is not a basement that can be rearranged whenever a developer needs more space. Its tracks, tunnels, electrical equipment, and operating rules determine where almost every major support can go. That constraint is where the story really begins. Developers did not buy an empty construction site. They acquired the right to build in the air above land already occupied by rail infrastructure. That legal concept is called air rights, the ability to use the space above a property while the ground itself remains in another use. Air rights can make a project possible on paper. But paper does not hold up a tower. Engineers still need a physical route for every pound of weight to reach rock strong enough to carry it. That route is called the load path. It is simply the journey taken by weight. Floors push into columns. Columns pass that force into larger structural elements. Those elements carry it down through foundations and finally into bedrock. In a normal building, engineers have considerable freedom to arrange that path beneath the tower. Over a rail yard, the path must dodge moving trains, signals, tunnels, utility lines, access lanes, and equipment that cannot be relocated. At Hudson Yards, only a limited part of the rail yard floor was available for structural supports. Official project diagrams put the usable area at about 38%, so the towers could not simply place columns wherever the architecture wanted them. The building above had to negotiate with the railroad below. The most important foundations are caissons. A caisson is a large shaft drilled through soil and weaker material until it reaches bedrock, then reinforced and filled with concrete. Think of it as a deep structural leg rather than a shallow footing. At the Eastern Rail Yard, hundreds of these legs were drilled into narrow spaces between active tracks. Many were roughly 4 to 5 feet wide and extended as much as 80 feet down, depending on where the rock was found. Now the puzzle becomes visible. A tower may stand hundreds of feet above the street, but its weight has to pass through a support zone only a few feet wide, placed precisely where a train will not hit it. Above those foundations sits the platform, a massive network of steel beams, concrete slabs, columns, and trusses. A truss is a framework of connected triangles that can carry heavy loads across a gap. Bridges use trusses because triangles resist changing shape. Hudson Yards uses them for the same reason. Where a support could not land directly beneath a building, trusses redirect the force sideways until it reaches a caisson that could be installed safely. This means the platform is not one flat table, with skyscrapers resting evenly on top. Some tower foundations pass through the deck and connect to carefully positioned supports below. Other parts of the neighborhood, including plazas, landscaping, retail areas, and portions of buildings, are carried by the deck and its transfer structures. The result is less like a lid and more like several bridges, foundations, and buildings locked into one three-dimensional puzzle. the scale is difficult to see from street level. Hudson Yard's eastern platform covers about 10 acres. Project materials describe more than 25,000 tons of structural steel, 14,000 cubic yards of concrete, and a completed platform weighing more than 35,000 tons before the full neighborhood above is counted. It bridges 30 working tracks, along with major rail tunnels beneath the site. Yet the railway continued operating during construction. That last fact creates the second major engineering problem. Building a bridge over trains is manageable when the line can close. Building an entire district over a rail yard that must keep serving New York is a scheduling problem measured in minutes. Crews could not occupy any track whenever they wished. Equipment could not swing through live electrical zones. A long steel member could not be lifted over a train simply because a crane was ready. Construction sequences were modeled around train movements. Work was divided into zones, with temporary protection over active areas and carefully timed access when tracks became available. Large components were fabricated in advance because the rail yard was a terrible place for slow, open-ended assembly. The strategy was simple to describe but difficult to execute. Do as much work as possible away from the tracks, then install each piece during a tightly controlled window. Manhattan West, immediately east of Hudson Yards, faced a similar problem but solved it with a method borrowed even more directly from bridge construction. Its public plaza sits above a broad rail corridor leading toward Penn Station. Instead of filling the track level with a forest of columns, engineers used deep, hollow concrete girders assembled from precast segments. Precast means the concrete pieces were manufactured away from their final position under controlled conditions. The segments were then joined and squeezed together with high-strength steel tendons. That process is called post-tensioning. It turns many shorter pieces into one long structural beam that behaves as a continuous unit. Specialized lifting equipment moved the finished modules into place from above. In effect, the team built sections of a highway bridge over the tracks, then used those sections as artificial ground for a city plaza. The trains below kept moving, while a new pedestrian route, landscaping, and towers emerged above them. Hudson Yards and Manhattan West therefore look like neighboring real estate projects, but structurally, they are two variations on the same idea. One threads deep foundations and steel transfer structures through a complicated rail yard. The other uses long bridge-like modules to leap over much of the corridor. In both cases, the architecture visible from the street is shaped by an invisible map drawn by the tracks below. But supporting weight is only the first half of the job. A deck strong enough for buildings can still be a terrible place for a neighborhood. Cover a working rail yard and heat begins to accumulate. Trains, electrical systems, braking equipment, and summer weather turn the space below into a large industrial heat source. That heat rises toward the plaza. Ordinary soil placed directly over the structure could become too warm for healthy roots, while trapped heat below would make conditions harder for railroad workers and equipment, so the park above cannot behave like a normal park. Hudson Yards addresses this with mechanical ventilation and a cooled landscape layer. Large fans move fresh air through the covered yard and remove heat. Above them, pipes carrying cooled liquid run beneath planted areas to protect root zones from excessive temperatures. The landscape is not simply soil poured over concrete, it behaves more like a giant rooftop garden with its own climate control system. The soil also has to perform several jobs at once. It must be light enough to avoid wasting structural capacity, deep enough for trees and shrubs, stable enough for thousands of visitors, and porous enough to move rainwater away from roots. Different plants require different soil depths, while structural designers must account for the extra weight added when dry soil becomes saturated after a storm. That detail matters because water is heavy. 1 cubic meter of water weighs about 1 metric ton. On a conventional park, rain can seep into deeper ground or spread naturally. On an artificial deck, every gallon needs a planned destination. If drains clog or storage fills too quickly, the water cannot simply disappear into Manhattan bedrock. It remains on top of a structure containing occupied spaces, utilities, and electrical systems. So the landscape also functions as water infrastructure. Rain falls on roofs and plazas, enters drains and planted areas, moves into storage, and can be filtered for reuse in irrigation or mechanical systems. This reduces the amount of drinking quality water used for jobs that do not require it, and it slows the surge entering New York's sewer network during storms. The ordinary appearance is the clever part. A visitor sees trees, paving, and fountains. The engineering system sees thermal insulation, drainage, storage capacity, root protection, structural load, and access points for maintenance. The park is not decoration placed on top of the platform. It is part of the machinery that allows the platform to function as land. Now, return to the train below. Covering the yard changes the way smoke, heat, and emergency access must be managed. A derailment, electrical fault, or fire can no longer be treated like an incident in an open-air yard. The covered space needs detection systems, fire protection, lighting, cameras, communications, and clearly defined routes for workers and emergency crews. Ventilation must operate not only for comfort, but also as part of the safety strategy. Meanwhile, the city above needs the same basic services as any other neighborhood: water, electricity, data connections, waste removal, loading areas, and mechanical equipment must cross a structure already crowded with beams and rail systems. This creates a problem that rarely appears in a normal street grid. A pipe or cable cannot be placed only where the route is shortest. It must also avoid critical structural members, preserve access to the railroad, allow the deck to move slightly with temperature, and remain repairable decades later. A hidden utility that cannot be reached without closing tracks is not a successful utility. Hudson Yards added another layer: a local energy network. A microgrid is a small electrical system that coordinates power generation and distribution within a defined area. The development also uses cogeneration, which produces electricity and captures heat that would otherwise be wasted, then puts that heat to work in hot water or building systems. The goal is not to turn the neighborhood into an energy island. It is to create options. During normal operation, the system can improve efficiency. During a disruption, operators may be able to prioritize essential services and support parts of the site with more control than a collection of completely separate buildings would have. The same principle applies to communications. Sensors can report temperature, power demand, water conditions, or equipment status. This is not magical smart city technology. It is industrial monitoring used at neighborhood scale. Measure what is happening, detect abnormal conditions early, and repair a small problem before it spreads. That matters more here because the layers depend on one another. If ventilation fails, heat can affect both the rail environment and the landscape above. If drainage fails, water threatens public space and equipment. If a structural joint develops a problem, reaching it may require coordination between property managers and railway operators. The platform creates valuable land. It also creates a permanent relationship between organizations that normally control separate worlds. And the platform alone cannot create a neighborhood. People still have to reach it. Hudson Yards became viable, partly because New York extended the No. 7 subway line west from Times Square, opening the 34th Street Hudson Yards station in 2015. The High Line, new streets, parks, pedestrian connections, and nearby Penn Station completed the access network. Without those links, the platform would still be an impressive structure, but it would be expensive land isolated at the edge of Manhattan. Transit does not physically hold up a single tower, yet it supports the neighborhood just as surely as the steel beneath it. There is also a support system no visitor can see: finance and regulation. Building over an operating rail yard is dramatically more expensive than building on an empty lot. The platform must exist before much of the revenue-producing development can rise. So enormous spending arrives early while returns arrive much later. Zoning changes, air right agreements, public infrastructure, tax arrangements, private capital, and long construction schedules all have to align. If even one layer fails, the engineering solution may exist without a viable project to use it. This is where the story becomes a city planning argument. Artificial ground allows New York to add buildings and public space without demolishing an active rail yard. It reconnects streets that once ended at an industrial gap and places offices, homes, and parks near major transit, but the cost of creating that ground tends to favor high-value development capable of paying for it. The platform is not automatically an answer to affordable housing, public space, or climate resilience. Those outcomes depend on policy choices made above the engineering layer. A platform can support luxury apartments, offices, parks, schools, or a mixture of all four. Steel and concrete do not decide who benefits. Nor does elevation eliminate environmental risk. Raising occupied space above a rail yard can reduce direct exposure to some coastal flooding, but the surrounding streets, tunnels, utilities, and regional power system remain vulnerable. A neighborhood cannot be fully resilient if the infrastructure connecting it to the rest of the city fails. And then comes the test that receives far less attention than the opening day: maintenance. These decks are not finished objects that can be ignored once the ribbon is cut. Steel coatings, concrete, drainage systems, bearings, expansion joints, fans, pumps, sensors, fire systems, and utility routes all age. Some of those components sit above active tracks, where inspection and repair are difficult and access windows are limited. The artificial land must therefore be treated more like a major bridge than an ordinary block of Manhattan. That comparison changes how the entire neighborhood looks. The plaza is a bridge deck. The gardens are a managed roof. The towers are carefully threaded into bedrock. The streets are part of a structural system. And the trains below are not leftovers from the site's past. They are an active machine around which the new city had to be designed. The unfinished western portion of Hudson Yards shows why this model is difficult to repeat. Plans for more housing, public space, and other uses have continued to evolve, but the next platform requires another enormous commitment before the neighborhood above can generate its full value. The engineering concept is proven. The remaining question is whether the financial cost, political effort, and public benefit can justify building the next piece of artificial Manhattan. So, what is the secret infrastructure supporting New York's newest man-made neighborhoods? It is not one hidden foundation, it is a stacked system. Bedrock carries caissons. Caissons carry columns and trusses. Those structures carry a platform. The platform carries utilities, streets, buildings, and an engineered landscape. Ventilation and cooling keep the rail yard and plants alive. Drainage and storage control water. Transit connects the artificial ground to the wider city, and long-term maintenance keeps the entire arrangement working after the construction crews leave. Above, it feels like ordinary land. Below, it is one of the most carefully negotiated pieces of urban space ever built. That is the real achievement. New York did not remove the infrastructure that occupied the site. It taught a new neighborhood to coexist with it. For more clear explanations of the engineering hidden behind modern cities, subscribe to Parallax Depth. Thanks for watching, and I'll see you in the next one.